Hello class, welcome to this tutorial. In this video we are going to see the precise definition of limit, that is also called epsilon delta definition of a limit. So we'll do some examples and exercises. So at the end of the class it is expected to prove a limit of a quadratic functions like x squared minus 5x plus 6 as x approaches to 4 equal to 2 using epsilon delta definition. Let's get started. As we know, the limit of f of x as x approaches to L, when we say this, f of x is nearer and nearer to L as x is nearer and nearer to A, if this limit exists. In other words, we can get f of x as close as you want to L by making x sufficiently close to A, but this is a qualitative meaning. We have to do a quantitative meaning. How much it is as close as means and also sufficiently close to A mean. So you need to have a quantitative meaning. For that we need an epsilon delta definition of a limit. This as close as means it is we are talking about distance, so we can express using absolute values. Thus the closeness of f of x to L can be measured using some variable. In our case we call it epsilon, so the distance from L is epsilon, and the distance from A, x from A, it is approximated by delta functions. So using this epsilon and the delta functions we can define our limits. It means if the limit exists, then we should be able to pick a number, in our case epsilon greater than 0, say for example an epsilon of 0.001, and we have to find some corresponding delta greater than 0, whereby whenever this distance less than delta, then we can be assured that f of x minus L, or this distance, is less than epsilon. In our case that is 0.001. so mathematically we can express this as, for all epsilon greater than 0 there must be exist some delta greater than 0 that satisfies whenever this distance less than delta. That means when x is sufficiently close to A, then we have to assure that f of x minus L is less than epsilon. So we have to close us to L if the limit exists. That is the definition of limits. It seems it is complicated, but when we do more examples it will be so simple. Keep following. Let's start by a simple example of a linear functions. A limit of 5x minus 2 as x approaches to 1 is 3. Let's prove this limit using epsilon delta definition. So we have to first identify A, f of x, and L. In our case f of x is 5x minus 2 and our L is 3, where our A is 1. So after identifying this one, to prove, first it's recommended to assume epsilon as given, and after assuming that we will find this f of x minus L, and if we manipulate this expression into x minus A and less than something, then we have known that the delta. So to prove this one we have to find delta. That's the final goal. So our goal is start from f of x minus L less than epsilon by assuming epsilon is given, and then finally to find delta such that it satisfies this one. Then we can rewrite the limit as backward expressions. Let's do that. So we start from absolute value of f of x minus L less than epsilon. So let's substitute f of x, that is 5x minus 2, and L is 3. So these expressions became 5x minus 5, and if we factor out 5, it will be 5 times absolute value of x minus 1 less than epsilon. Our goal is to manipulate this one into x minus a. In our case, our a is 1, so we try to manipulate these expressions into x minus 1. So we got that less than something. Our something is epsilon over 5. It means from the definition of epsilon delta definition, the distance from a, x from a is delta, so it means in place of delta we get a number epsilon over 5. So we can choose a delta epsilon over 5 for this number. So we can rewrite these expressions as for any arbitrary epsilon greater than 0 that we have assumed before. So for any given epsilon, if we let a delta which is epsilon over 5, then this expression, that means x minus 1, whenever this expression satisfies, we can be assured that f of x minus L must be less than epsilon. So if we do that, we have completed our proof. So rewriting backward, x minus 1 less than delta, and then this delta is chosen epsilon over 5, then making crisscross, it will be 5 times x minus 1, and this 5x minus 2, we try to manipulate this one in terms of f of x minus L. So we got the form. So if we got these expressions, it means for every epsilon greater than 0, there exists a delta which is epsilon over 5. Whenever these expressions happen, then we can be assured that f of x minus L is less than epsilon. So this completes our proof. Let's continue for quadratic functions. For quadratic functions, for example, in our case, x squared minus 5x plus 6, as x approaches to 4, we know that if we substitute 4 in place of this one, we got 2. So how are we gonna prove this limit? As we done before, let first identify f of x, that is x squared minus 5x plus 6, and our a is 4. We know L is 2. Then assume that epsilon is given and try to manipulate f of x minus L in terms of x minus a less than something. So after identifying this, we try to manipulate, start from f of x minus a less than something, and we try to get x minus a less than something. So let's get started. Our f of x is x squared minus 5x plus 6, and our L is 2, so it will be x squared minus 5x plus 4, and then this expression can be factored out as x minus 1 times x minus 4. Our a is, we know that 4, so we try to manipulate this one as x minus 4 over this, both sides divided by absolute value of x minus 1, it will be epsilon over x minus 1. So as we done before, we got x minus a less than something, but here there is a term x, but this our delta must be written in terms of epsilon, not with a variable of x. Since we know that when we talk about limit, it means when we close to a. So our a is 4, then restrict this x, and after that, after restricting this x value from a, we can find this absolute value of in terms of number. Let's do that. So after we do that, let's first restrict this x minus 4 within the range of 1. If we do that, this means minus 1 less than x minus 4 less than 1. It means if we plus to all sides 4, so it will be 3, this will be x, and this one will be 5. This means we try to manipulate this expression x minus 1 absolute value in terms of number. So after getting x, let's do for x minus 1. So to make it x minus 1, subtract to all sides with of minus 1, so it will be this one minus 1, it will be 2, and this will be x minus 1, and this one will be 4. So this x minus 1 will be in the range of 2 and 4. So how could we express this epsilon over absolute value of x minus 1 in terms of a number? So let's do epsilon over these expressions, and we can get that this inequality will be reversed, and it will be epsilon over 4 less than epsilon over this x minus 1, which is the same as absolute value, because x minus 1 is in the range of 2 and 4. We can write x minus 1 or absolute value of x minus 1. They have the same meaning to these expressions, and it will be less than epsilon over 2. Now we know that epsilon over absolute value of x minus 1 is always greater than epsilon over 4. So we can write the above expressions as this one as less than epsilon over 4, because this expression is always less than epsilon over 4 if we restrict our x from a to 1. So this means we can choose a delta epsilon over 4, but we have to have two restrictions. The two restrictions are this one epsilon over 4, and we restrict our x minus 4 to the distance of 1. So we choose this delta to be the minimum of this one and this one. If 1 is, for example, it is the minimum, so we choose 1. But if epsilon, for example, if epsilon we choose 3 over 4, it is minimum that of 1, so we will choose this epsilon over 4. So delta should be chosen as the minimum of 1 and epsilon over 4. Then after getting delta, then we know our number from our this assumed epsilon. That means we can rewrite this proof inversely. Let's do. So for a given arbitrary epsilon greater than 0, we can choose delta that is a minimum of 1 and epsilon over 4. Suppose, for example, the minimum of those two is 1. Then this means delta equal to 1. It means 1 is epsilon, from epsilon over 4 it is less than, so it means when we crisscross it, epsilon is greater than 4. Then this x minus 4 less than delta can be written as less than 1, because the minimum is in our case 1, and this epsilon is greater than 4. Thus we can multiply both sides by x minus 1, and this x minus 1 is less than 4 because we already done before, and then these expressions will be less than epsilon. We know it because this absolute value of x minus 1 we have done it before, and this absolute value of x minus 1 is less than 4 always if we choose delta is 1, and this 4 is, we know that, less than epsilon because 1 is epsilon over 4. Thus this expression is written as x squared minus 5x plus 4 less than epsilon, and it will be x squared minus 5x plus 6 minus 2. We done this because to make rearranging this as in form of f of x minus L, then we have done it. So starting from x minus 1, that means whenever x minus 4 is less than delta, we can be assured that f of x minus L is less than epsilon. For every epsilon we can get a delta equal to 1 if the minimum is 1. But what if the minimum of 1 and epsilon over 4 is epsilon over 4? So we have to rewrite for that case also. So let's write if the minimum is epsilon over 4, that means we start from x minus 4 less than delta, and our delta is now chosen as epsilon over 4. So once again, we know that x minus 1 is in the range of 2 and 4. We have done before. Thus, multiplying this one, it means x minus 1, this x minus 1 multiplying here, and less than 4 times epsilon over 4, because we done that because this x minus 4 is always less than epsilon over 4. Thus we can multiply by x minus 1 and we can multiply his 4. That can be satisfied because we use these expressions here. When we multiply these expressions, it becomes x squared minus 5x plus 4 less than this 4 by 4 cancel, and epsilon. We can so manipulate these expressions as f of x minus L less than epsilon. Here we use these expressions to x minus 1 is in between 2 and 4, and then from this starting point we multiply this one by absolute value of x minus 1. So if we multiply by that, we have to multiply by 4 here to be assured that this is satisfied. So we can come up with final expression of this one. So whether delta have a minimum value of 1 or a minimum value of epsilon over 4, whenever this x minus 4 less than delta happens, we can be assured that f of x minus L is epsilon less than epsilon. So we can rewrite this one. It means we have completed our proof. So for quadratic functions, rewriting have two expressions, two cases, because we have an expression of a minimum of some restriction and also two restrictions. So for this restrictions we will do as such. This is a way how to prove these expressions. So do these exercises. If you have difficulty, we can do this one together. For today it is enough. If you have any questions, you can write on comments. Have a good day. Goodbye.